Transformations, are they cooked? Absolutely.
Oh no, we are cooked.
So let's try and create a way to think about them a little bit easier. Now, we have our three transformations that we can apply in the VC. We have our dilation, reflection, and our translation. Here, we want to think about what each of these does to the function geometrically. Sure, we want to care a little bit about the wording, a bit of it, the intuition, but it's mostly literally the exact same thing as U substitution, where you sort of look at it and you get the answer. Like, it's not that crazy in depth, but you need to be able to realize what each transformation does. So first thing, the dilation, what does that do? The dilation, we pull it away from an axis. The phrase we like to use is a dilation by a factor of something from the something axis, or horizontal axis or vertical axis. We want to use the phrase horizontal and vertical axis in order to just avoid losing those simple marks. Because sometimes in questions they can care about context a little bit, where it's not the x-axis, it could be the t-axis or the z-axis or something else because they're douchebags. Thanks, Vicar. Now that we've gotten dilations out of the way, here's a little bit of a graphical depiction of each of these ones, just in case you wanted to see what they look like when we change the value of, let's just say, our dilation by a factor of a. What happens when a changes? And we can see when we stretch it from the x-axis, it becomes bigger in the y values. The y values become bigger when we stretch it away, and when a becomes smaller, we compress it down and the y values become smaller. So this is where we need to realize that here, a dilation from the x-axis actually affects the y values, and a dilation from the y-axis actually affects the x values. Very intuitive, I know. The phrasing isn't confusing whatsoever. Now, the next thing we have to deal with is reflection. There's three reflections we deal with. A reflection in the horizontal axis, a reflection in the vertical axis, and a reflection in the line y equals x. Now the last one is for inverse functions, so it's not that much of a big deal. It's more of just a property of inverse functions you need to remember, so we won't cover too much of it. Here, we need to think about, well, what does a reflection in the x-axis do? Well, it flips it over. It affects the y values here when we flip it about the x-axis, as you can see by this graphical interpretation here. Now, if we look at a reflection in the x-axis instead, we can see that here is our graphical interpretation. I just said the same thing twice. Here is what happens when we reflect it about the... I don't know why I'm struggling so much with the wording. Here is what happens when we try and reflect it about the y-axis instead. Do you see how here for the y-axis it actually affects the x values, and when we do a reflection in the x-axis, we are reflecting the y values. We need to realize these, again, very intuitive, very straightforward. Thanks, Vicar, for making it very simple. This is why we choose to take a geometric approach to these sorts of things, recognizing what these actually do rather than trusting the wording, because the wording's a bit So, next thing, translations. Translations are pretty straightforward. We can either have a translation to the right, to the left, up or down. So we do translation by something units to the right or left, blah blah blah. Pick your direction. Now, as you can see, this is just going to be a very basic one here. It's pretty straightforward when we're translating it up and down, left and right, as long as you know your lefts and rights, like you're not doing this shit mid-exam. I mean, you can, I'm not going to stop you, but if I was on your vigilator, I'd make fun. Just be able to tell those things apart, be able to tell, well, do I want to move it to the left or do I want it to be able to move it to the right? So then, now that we've gone over those ones, we want to look at our two methods we can actually apply these transformations onto functions, aka points. So the first thing I want to look at is actually going to be mapping method. Now, mapping method is very underrated nowadays in the VCE exam. We usually use function notation, which makes the other one more promising. However, mapping method is the derivation you need for function notation. For mapping method, every transformation can be applied in these ways, as this table shows. So we have these things, and it's very straightforward. If I do a dilation by a factor of a from the x-axis, this point changes from x comma y into x comma ay, because we know a dilation from the x-axis affects the y values. and we say that AY to say that A is the dilation factor. If we want to do reflections instead, as we can see in the table here, if we do a reflection in the horizontal axis, we're going to instead have x comma y, which now becomes x comma negative y. As we see, the reflection turns the y values into a negative. Last thing for translations, here we can have a translation by a units in the positive direction. In the positive direction of the vertical axis. If we do that, x comma y becomes x comma a plus, x comma y plus a. Here we can see that these transformations, literally as we're told them, we can apply them in the way that, it's very straightforward. These transformations, when we're told them, we can literally apply them in the exact way we're told them. If it says positive direction, it means positive direction. So we put the plus a. If it says negative direction, we put the negative direction. Negative a. If we want to do a reflection, it's just a simple negative. If we want to do a dilation, it's just a simple times by a. And we usually use this one for points. We usually use this one for point transformations if we're transforming a point. So if we want the final version of, if we want to apply all our transformations at the same time, this is what we can use up here. I'll show you this one. So it is x comma y becomes ax plus b comma cy plus d, where a and c are both dilations and b and d are both reflections. Now here obviously it doesn't show the reflection here, but the a and c can change signs from positive and negative to show the reflection. So we sort of think of a reflection as a special form of dilation, essentially. Now that we've gone over the mapping method, the big thing I want to look at now is the function notation, which is slightly different, as we can see by this table. This table is a little bit different as we can see our y transformations, anything that changes the y value, so a reflection in the x-axis, a dilation in the x-axis, they all will be the same as mapping method. They're very intuitive. However, here, for function notation, we do this thing called we don't trust our x. For example, if we're given a translation by a units in the positive direction of the x-axis, here is the transformation we apply, where f of x becomes f of x take away a. It doesn't make sense, but that's essentially saying we're doing it in the positive direction. This is where function notation, you want to be a little bit more careful with it. Whenever it's inside the f of x brackets, we don't trust it. So if it says a dilation by a factor of a from the y-axis, here we actually do f of x becomes f of x over a. This is the sort of intuition we need to be focusing on. This is the sort of thing we need to just be able to see here. It will be a little bit complicated at the beginning, but once you get a handle of these two methods, they actually become very straightforward to use. Now, we can focus a little bit on the application of things. The big thing that's been showing up a little bit more is integration transformations, as everything else has been on the study design for a long time. So integration transformations, the reason I want to focus on them is because of how it changes the area. For example, if I do a dilation by a factor of, let's just say a from the x-axis, yeah, that means I'm making it taller. I'm making the area taller. I'm basically timesing the area by a in this case. This is where we start to realize the applications of transformations aren't as straightforward as they seem. As you can see, we've been dealing with functions for most of this time, but now I'm applying it to areas. Essentially what I'm saying is when we apply a transformation, we can apply the transformation in multiple different ways, but they will have the exact same effect. We can apply it onto areas, we can apply it onto functions, we can apply it onto shapes, so on and so forth. This is where, again, geometry reigns king. You want to be able to draw all of these out. You want to have a go at sketching these. And if you want me to go over how to be able to do transformation questions, comment below, I will make a video on it. So, now, let's ask our good friend, the Dragonair. Is this Dragonite? I don't know. It's not fair. It's a Pokemon. How much did you learn from this video? Oh, nothing? Great, go do some practice questions. Bye.